So here's another function where the top of my fraction is a squared polynomial and the bottom of my fraction is linear. So I'm expecting a non-horizontal asymptote. Can we simplify? We can factorise a little on the top. X plus 3 over x minus 1. But again, there's no common factors top and bottom, so I can't go further. All right, ideas. What are the intercepts? Well, for the y-intercept, set x equal to 0. Y is, if it's 0, then this whole top of the fraction is going to be 0. So I've got 0 over negative 1, or in fact just 0. So it goes through the origin. For the x-intercept, well, I know one of them already. One of them is going to be 0, 0. But let's see what else I can find. If y is 0, that's x plus 3 over x minus 1. I don't care about the bottom, it's the top that has to be 0. x plus 3. Well, if that's 0, then either x is 0, which I already knew about, or negative 3. So they're my two x-intercepts. Discontinuities. My graph is discontinuous where the bottom of the fraction is 0. Where x minus 1 is 0, i.e. x equals 1. So that's going to be a vertical asymptote. All right, extremities. I'm expecting a non-horizontal linear asymptote. Extremities. As x approaches plus or minus infinity. Well, remember how we worked it out last time? I have to actually do this division to turn my improper fraction into a mixed polynomial fraction. So let's do the division. X squared plus 3x divided by x minus 1. That x goes into x squared. X times x is x squared minus x. Subtract. That's 0 is what I wanted. 3 plus x is 4x. X goes into, there's nothing to bring down, by the way, notice. I can go plus 0 if I like, but there's no constant term at the end. X goes into 4x 4 times. 4 times x is 4x. 4 times negative 1 is minus 4. Subtract. That goes away, 0 plus 4. So my remainder is 4 over x minus 1. So that means my y, which was x squared plus 3x over x minus 1 is, that division is, this quotient and this remainder. And now I have a mixed numeral, in quotes. It's a mixed polynomial fraction. There's my quotient, there's my remainder. Now remember, we're looking at the extremities. As x gets very large, this on the bottom here is going to get very large, so this term is going to get basically 0, very close to 0. And I'm going to be left with x plus 4. So y equals x plus 4 is an asymptote. Whoops. As x approaches plus or minus infinity. But notice again, the graph will not cross this asymptote because this is not 0. This can never be 0. So the remainder I've got left will mean it's always a little bit different from this. Alright, I haven't gone quite as far on my scale as I did last time. I think this should be enough for us. Let's have a go. Y-intercept in the origin. X-intercepts at 0 and -3. We already knew that one. And this one, -3, 0. I have a vertical asymptote at x equals 1. I have a slanted asymptote at y equals x plus 4. That's a diagonal line like this, try and get it close to gradient 1 and going through 4. And I should label my asymptotes. X equals 1 and x equals, y equals x plus 4. Okay, so my graph goes through these two, never crosses these asymptotes. So it must be coming up very, very close to this asymptote there, going up and over, and then going down there. It's not actually straight. Should have curved that one a little bit. So the other side, it's going to do the same thing. Going to come down very close to there, curve round about the same distance, and go back up close to that asymptote, getting closer and closer and closer. And that is, I'm going to have just enough room there. I think y equals x squared plus 3x over x minus 1. And again, if you wanted to, you could differentiate this function to work out the positions of those stationary points.